Bismillahirrahmanirrahim. Assalamualaikum. My name is Yasmin. So today I'm going to present the introduction of our topic. So nanomaterials defined as material with at least one dimension in the nanometer scale, which is 1 to 100 nanometer, have emerged as a cornerstones of modern technological advancements. So their unique properties, there are few unique, which is increased surface area, quantum impact, and enhanced mechanical, electrical, and thermal properties. And it also have a few applications in electronic, medicines, energy, and environmental science. The types of nanometer, they have carbon based, metal based, semiconductor, and polymer based. It also, in this topics, it also have fabrication methods, which is top down and bottom up. So they have a few challenge in this report. By analyze this aspect, it can gain insight into how nanomaterials can be optimized for specific application. Through this lens, we can develop into a transformative potential of nanomaterial and ongoing quest to integrate them seamlessly into the fabric of advanced technology.
Assalamualaikum, my name is Aisha. Now we're going to proceed with details types of materials. So let's start with carbon-based nanomaterials. The first one is fluorinous. These are spherical molecules made up of carbon atoms arranged in hexagons or pentagons. Despite their potential high production costs and functionalization challenges limit their widespread use. They are primarily used in drugs delivery systems, superconductors, and as antioxidants. Next one is carbon nanotubes or CNTs. These cylindrical structures are formed by roll-up sheets of graphene. The applications include reinforcing materials and components in energy storage. However, controlling their wall structure and ensuring purity during synthesis remain significant challenges. Last one is graphene, and is known for its single layer of carbon atoms arranged in 2D honeycomb lattice. Graphene is used in sensors and conductive inks, and the primary limitation is in the difficulty in large-scale production. Next, we have metal-based nanomaterials such as gold, nanoparticles. These can vary in shape based on the synthesis method. They are used in medical imaging and drug delivery, though their high cost and potential toxicity are notable drawbacks. Then is the silver nanoparticles. These are known for their antimicrobial properties and are used in coatings and textiles. However, the environmental impact and toxicity to human cells are a concern. And last for metal-based nanoparticles is platinum nanoparticles. And despite their high cost, they are crucial in catalytic converters and fuel cells. Semiconductor nanomaterials include quantum dots, silicon nanowires, and zinc oxide nanoparticles. Quantum dots, while they hold promise for medical imaging and quantum computing, the toxicity of cadmium used in their synthesis is a major limitation. Silicon nanowires are vital for high performance transistors but face integration challenges with existing silicon technology. Zinc oxide particles used in UV blocking coatings and they have issues with stability and potential environmental impact. Lastly, let's look at polymer-based nanomaterials such as polymer nanocomposites. This consists of polymers with dispersed nanoscale fillers like clay or carbon nanotubes. They are used in automotive and aerospace industries, but achieving uniform dispersion of nanoparticles is difficult. And lastly is dendrimers. With their highly branched tree-like structure, dendrimers are used in drug delivery system and as gene transfection agents. Their complex synthesis and potential toxicity are key limitations. That is all for me.
Next is on the physical properties of nanomaterials. Nanomaterials have a unique physical properties that differ greatly from bulk materials due to their nanoscale size, high surface to volume ratio, and a distinct atomic structures. Here I have divided into four categories, which the first one is mechanical. It enhances it has increased in strength and hardness due to their nanoscale grain boundaries. Nanocomposites formed by embedding nanoparticles in a matrix and have superior properties due to the transfer of fluid and bridging between the cracks. Next is the high elastic modulus. However, it can be varied with the size due to the changes in atomic arrangements. The third one is the deformation mechanism. The deformation mechanism of nanomaterials is often caused by sliding of the grain boundary, diffusional creep, or twin boundary migration, while amorphous nanomaterials are usually deformed by the formation of a shear band. And the last one is increase in wear resistance. With nanocrystalline coating, it enhances surface durability, and some nanocomposites even showing their own healing properties, repairing cracks to avoid further damage. And then moving on to the optical properties, first is the quantum confinement, where dots show size-dependent emission wavelengths. Metal nanoparticles display surface plasma resonance, which is SPR, in resulting in a strong light absorption and a scattering at specific wavelength. The second one, it enhances photoluminescence, which is beneficial for imaging and sensing application, and their emission properties can be tuned by altering their size. And the third properties is the electrical and chemical, which for the electrical, it has a high electric conductivity and electron mobility, which due to their unique electron structure, and this is beneficial for high-speed electronic devices. And as for the chemical properties, it has a high chemical reactivity due to their large surface area to volume ratio, which enhances their effectiveness as catalysts. Their surfaces can be functionalized to tailor chemical interaction, benefiting in sensors and drug delivery system. And the last properties is the thermal properties, which it has a high thermal conductivity, but it has a size-dependent conductivity characteristic, which it varies with the size due to the phonon scattering and other nanoscale effects. And then the last one will be it has a great thermal stability due to the high surface energy and strong bonding. The thermal expansion coefficient of nanomaterials can differ from bulk materials, affecting their behavior under the temperature changes. Next, moving on to the microscopic characteristic of nanomaterial. There are four, which the first one is the grain size and boundaries. The small grain size in nanomaterials significantly influences their properties, with grain size boundaries crucially affecting mechanical and thermal behavior. Second is the surface effects. The high surface-to-volume ratio of nanomaterial lead to significant surface effects, impacting reactivity, mechanical properties, and thermal stability. Surface functionalization further enhances their versatility and application potential. And the third one is defect structures, which nanomaterials typically have a lower defect density, yet the presence of point defects and vacancy can still substantially influence their properties. And the last one is the crystalline versus amorphous structures, which crystalline nanomaterials display a high strength and modulus owing to their ordered atomic structures, which give rise to unique deformation mechanism.
Now, we move on to the mechanical properties and microstructures of silver nanomaterials. The materials processing method is chemical reduction. Chemical reduction is the reduction of silver salts using chemical agents such as sodium borohydride and citrate. The mechanical properties are high strength due to the small size. The microstructures properties are usually phase center cubic or known as FCC. Now, we move on to the mechanical properties and microstructures of. The next material processing method is laser ablation. Laser ablation are ablation of silver target using a laser in a liquid medium. The mechanical properties are usually increased hardness and strength. The microstructures properties are usually in the crystalline structure. The next material processing method is laser ablation. Laser ablation are ablation of silver target using a laser in a liquid medium. The mechanical properties are usually increased hardness and strength. The microstructures properties. Next, the material processing method is physical vapor deposition. The silver is vaporized and deposited onto a substrate. The mechanical properties can be enhanced by undergoes the materials processing method. The microstructures properties are usually high crystalline quality. Next, the material processing method is physical vapor deposition. The silver is vaporized and deposited onto a substrate. The mechanical properties can be enhanced by undergoes the materials processing. And lastly, the material processing method is biological synthesis. This process undergoes by utilizing biological organisms such as bacteria or plants to reduce silver ions. By undergoes reprocess, the mechanical property is biocompatible and the microstructure's properties are usually in biogenic shapes. And lastly, the material processing method is biological synthesis. This process undergoes by utilize biological organisms such as bacteria or plants to reduce
Hi, my name is Brenda and I'm going to present on fabrication process and its application. So there are two fabrication methods that are widely used, which are top-down methods and bottom-up methods. And I'm going to elaborate two examples for each method. The first is top-down method, where it involves breaking down bulk materials into nanoscale particles. So these methods, they are typically used when precision and control over final product's shape and size is crucial. So the first example is dry etching. It uses a plasma or reactive gases to remove material from a substrate surface. So it is capable of achieving small feature size, which is essential for detailed patterning. Its application is usually widely used in semiconductor industries for patterning and structuring integrated circuits (ICs). The next one we have ball milling. It involves grinding bulk materials into finer particles using mechanical force. So this method, it can produce nanoparticles by repeatedly fracturing and welding the particles. It is ideal for with mass synthesis of nanoparticle with mass or excellent purity. It is frequently used to incorporate is frequently incorporated into polymer matrices to produce nanocomposites with enhanced properties. Now, moving on to the bottom down methods, it is a method that involves assembling materials atom by atom and or molecule by molecule. So this method is typically used when precise control over final product composition is necessary. The first one is sol gel. It is a method that involves transitioning a system from liquid sol to a solid gel phase. So it is considered the easiest technique for synthesizing nanoparticles. It's commonly used to create thin films and coating, also biosensors and biomedical implant. The last one we have electrochemical. It is a process that uses electric current to drive chemical reaction that produces nanoparticles. It is simple, effective, and cost effective. Usually used in water splitting and hydrogen production. It can also be used for corrosion protection. That's all from me. Thank you.
So, for the conclusion, nanomaterials have ushered in a new era of scientific innovation by harnessing the unique features that result from their tiny dimensions. Carbon-based, metal-based, semiconductor and polymer-based nanomaterials all provide significant advantage that are used in a variety of applications in medical, electronics, energy, and environmental science. Nanomaterials' outstanding physical features such as higher mechanical strength, high elastic modulus, greater wear resistance, quantum confinement in optical properties, superior electrical conductivity, and also high thermal stability that play an important role in driving innovations. These features are due to their high surface to volume ratio and distinct atomic configurations that differ greatly from those found in the bulk materials. So, top-down and bottom-up techniques are both important in fabrication process. Top-down tactics are demonstrated by techniques like dry etching and ball milling, while bottom-up strategies are highlighted by slow gel and electrochemical produce. To summarize, nanoparticles' unique features are diverse fabrication methods that make them indispensable in technological advancements. So, by understanding their compositions, processing methodologies and restriction in critical for realizing their full potential and overcoming the obstacle they bring.